Greetings and welcome to another demonstration. And this one is a very full-featured machine learning demonstration that uses actual signals off of your board. Uses digital signal processing to collect the data, the signals, and we create signal files to upload into NanoEdge AI Studio to create a machine learning model or library and deploy that into a STM32CubeMX project. And anyway, this one has several modes. I'm going to show you how to collect the data. I'm going to show you how to change the mode into testing the data and inferencing against the model. And then the final mode is running in a self-diagnostic mode where you're regathering data from your machine, from your device, and running it through the model and looking for outliers. So it's an outlier detection application. So it features a reusable buffer architecture to reduce SRAM and so you don't blow your stack and so on. And then also for testing, I have a very big two-dimensional array, but I have that conditionally compiled out. But even when you compile it in, I use the const qualifier so that it ends up being in the data section, in the SRAM. And then the reusable buffers kept me under 4 kilobytes buffer usage for the entire application. Also, I use 6 different signal files to train the model, each specific for the signals that we're collecting off the device. And so that is using a multi-filed experience, as it's called in NanoEdge. You get good results against all those different types of signals, even though they're different from one from another. So switch over to my README. So I'm collecting voltage, from analog to digital conversions, temperature and I'm using the digital processing library. And by the way, I have that configured and it's included in the driver's file, so you don't have to worry about hunting it down and configuring it. I've got it all copied in and I might have a few hard-coded paths in the includes and in the library that you might have to fix in your project. But it's all there. CPU load, it's a cycle counter and so on. Trend analysis. RAM use, really it's stack usage because I don't dynamically allocate an embedded system. Power draw, the MCU core temperature, which is related to this internal. It's going to have the same type of data as the internal sensor. A loop jitter, and so I'm using like fast Fourier transform and different filters from the DSP library. I didn't submit the UART traffic because I didn't want to disrupt the flow with depending on an external COM port send. So I didn't want to create that. So I really don't have this. I got the code for it, but I didn't really turn it on. And then analog, basically ADC floor noise. I didn't turn this on either because it produced some what I think were legitimate infinity readings, which is an INF is a legitimate float value, but NanoEdge didn't like it, so I didn't add that to the model. The code is there though, so it does run though. I have a DSP mode where you can run all of this stuff and it prints and you can look at all the results, but it's not all of them are part of the model. I think 6 of them are part of the model for doing the machine learning. Internal clock drift, so on. And so yeah, the 4 different modes. I don't know if you want to look at code or show you a demo, but I want you to hang in there because this is people who are interested in this are pretty niche. And so this, I've got a good project checked in. You should be able to clone it, follow along, and really learn a lot. Plus, I've got some good programming principles also. It's a big multi-file project. Show you how to divide up your modules and how to reuse your buffers, so you're not creating a buffer in every file or for every function. And I have a interface for doing that to keep everything organized. So you have DSP mode, and that's just for, I'm getting those signals and we're just processing them, running some DSP library function on it, whether it's FFP or getting magnitudes or jitter measurements or filtering, normalization of a signal, whatever it is. And then we just print that out. And then I have signal format, and that is basically, I gather that data and then I pipe it out into, and so we gather that and I let it run overnight, so I get 500 samples, basically, 100 or 600, 100 for each signal, and that becomes our data that we use for training the NanoEdge model, and then also that's the test data for inference dating. So I have a big array with that same exact data that we pipe through the model. Then once it's trained and once it's tested, then we go into self-diagnostic mode or whatever, and we have trained model. We don't use the hard-coded inference data anymore. Now we're gathering the signal data from the device again, and we're piping that right into the model and getting an instant result and seeing if we have an outlier or not. So you could think of DSP as verbose logging, where you're seeing the whole state of it. And so I have everything. If you want to do this from scratch, I have some files for you to use if you want, or it's pretty, I'll show you when we look at the code how to do that. And then, so now I think it's time to look at the code. And by the way, I have a COM port reader. I'll show you that. That's in the READ. The README is more explanatory. I have a COM port reader that's a little bit friendlier. The text is displayed by Jonathan Valvano. It's very stable and great. But when it saves a file, it saves it to a hard to parse format. Anyway, you can use Notepad or Notepad++ to fix that, but my COM reader reads this text and it's easy to do stuff with. I still use Notepad++ though to kind of remove some tags I use for identification and so on. So let's look at some code. And by the way, I'm targeting just a STM32F401RE, so it's not some big high capacity board. I'm amazed at how much functionality I was able to get on this board, and with plenty of room to spare if you lay out your code wisely and use your buffers wisely and make sure you write certain things to SRAM with const qualifiers, and then choose the right model. And this NanoEdge Studio really produces a small model. I have another video that people like to watch where I get a Keras model onto a microcontroller, but that's very resource heavy. I had to use a H7 board for that to work. And this is the way to go moving forward for microcontrollers, I believe. So right now, rather than having runtime control of these modes I'm speaking of, I'm using conditional compilation. It's just more stable, so you can compile it and run with these different flags. And I'll show you where those flags are. So I have this file called dsp_test.h, and it's pretty much all my includes are here, and all my forward declarations are here, and a lot of my macros are here. And so 128 is the number of elements in my training model and inference model, and you can set that in NanoEdge Studio. But anyway, so here's the I have these commented out. So there's DSP test, signal format, inference test, and what I have running is self-diagnostic mode. And you can just run it in this mode because you don't need to. If you use the library that I checked in, if you have a STM32F4 board, it's going to work. you can just run it and use the library, have the library checked in, and the model library checked in, and the headers, everything. You can just run it in this mode and do the lifetime. You don't have to go through all the steps of generating the signal data and testing the signal data. But that's here if you want to. And so again, here's main. And so this is all signal format is about creating the data. DSP test is about validating the data the first time through. It's verbose. You want to make sure you're in the ballpark. And then once you have that, then you can run the signal data. The inference test, what it does is it initializes the model, and then it runs this big array. So in inference data.c, I have this 495 row by 128 columns. That's 128 is the important number of comma delimited data formatted into a two-dimensional array. But I do conditionally compile it because this is big. If I did not have this float, if I didn't have the const qualifier, it would not link. It's just too big. And so anyway, if you put the const qualifier, it gets written to SRAM into the I should mention before I forget, make sure you get my linker file, because I add a variable to get it at runtime. Here, let me show you that real quick. Apologize, the font size here is very small, but I've got my minimum heap size set to 1000 hex, same with the stack size. But I have this _stack_start that points to e stack minus min stack size, so it'd get the lowest address of the stack. And so then I can get this at runtime for my stack test. So when I'm testing the inference, I just run this big array through an inference function. Now the interface is here, the NEAI1 class. That's an interface of the model. Here, we'll take a look at that real quick too. So when you deploy the model from NanoEdge AI Studio, it produces, there's three main files. There's the lib neai.a that you put into your lib path, and there's this header called NanoEdge AI.h, and so gives you the access number, and the that's basically means 128 is the column, and it's like one row by 128 columns is one record to pass to the API. So you have to call this a init class, and you pass in the knowledge. And so knowledge, you're getting the trained data in outlier. You don't get a choice. That is it's an array. Here, we'll take a look at that. Here it is. So here's your knowledge. And so this is your initialization call. So there's only two calls. You pass in that it's called knowledge. You pass in the knowledge buffer. And then this is your inference call. You pass in a floating point array of 128 floats. And then you pass in an out param. It's an integer, but it acts as a Boolean. Is it an outlier or not? And so back to the inference test that's running that big array. So I'm looping through it. Data rows is 495. That's how many rows are in that array. And then I have to use a temporary buffer though, because I have to use an auxiliary buffer. It's not temporary, because the API won't take a const float. So I memcopy it into a reusable buffer. So we can talk about the reusable buffers right now too. So dsp_test.c is where I have a lot of the common functions in a separate compilation unit. Basically, running the tests is an array of function pointers. In case I wanted to loop it, I'm not doing that now. I'm calling them individually, but it's right here. Now, the buffers are generic looking, but I have a class. So I have this class right here, struct RU means reusable, underscore vec means vector. It's not really a vector. It doesn't grow. I have these two. I really don't even need these two len and capacity variables. I ended up not using them. I have an assert macro that I could put in here, but what it does is you declare an instance of this structure and then you call init, and so you pass in a reference to your struct instance and then one of these generic looking floats. So it's the structure instance is the name that describes what the buffer's doing, but you use a generic looking buffer that's specializes more on its size. So we have three 128 float buffers. We have one for 256 for fast Fourier transform. And then for timestamps, I needed to add a uint32 buffer. And then I didn't want to mess with the coefficients, so that's just hard-coded. And the same thing with the state. I didn't have a buffer that matched it, so I went ahead and left that. But anyway, here are those helper functions implemented. And so we mem copy into the reusable buffer structure class, RUVec, into its member called pbuff. And we're going to, the signal data is that big array that's in its own compilation unit, the inference data.c, the big 494 row by 28. And so we copy one row into it as we're looping through it. It's 128 times the size of float because they're floating point. Then we make the call and we tally up whether it's an outlier or not, and we print out some status. And that shows up in your COM port reader, whether it's PuTTY or the Texas display or mine. Then we have the tally there at the end, and that's how you test it. And you get an idea of, when I ran it out of 495 rows, I've got 26 outliers. However, when you're in self-diagnostic mode, that is when you pull the data and get fresh data, and you're not using that big buffer. You're using actual data off the board and running that through the trained model. We have a different pathway to do that. So here in this test voltage, we're going ahead and we're getting the data. We're pulling it through the analog to digital conversion function and we have these reusable buffers we're using to store the results. We're running them through DSP functions. We're doing a FIR filtering of the raw samples. And then we're preparing for fast Fourier transform with the interleaved complex array. We're basically we zeroed it out so we don't have to explicitly put in a 0 for the imaginary number. That's a common pattern for preparing for fast Fourier transform. You should put the actual float that has a value into the real, and you put a 0 valued float into the imaginary, and then you pass that to fast Fourier transform, and it populates the imaginary field for you. A different view, more of a time view, if you're looking at it on a XY. Anyway, I don't want to get too much into that. So then, here we go. So if self-diagnostic mode is being compiled, then we pass, the call is one inference, and we just pass the entire buffer with a message so we know who's calling it. And in main, we have one inference, so we pass in that float. I have it hard-coded to 128, so you don't pass a wrong size buffer to it. It's kind of a poor man's type checking. We make the call, and then again, if it's an outlier, we increase the totals. If not, we increase the pass, and we print it out. And also, if it is an outlier, we print out every value so you can see the pattern in case you want to inspect it. So this is kind of like a inspection mode. Now the sig print function you'll see scattered throughout all the test code is only it's only actuated, turned on when signal format is the mode. And what it does is it prints in the format that the NanoEdge Studio expects. That's 128 rows with space delimiters. And then I do prepend with a tag that tells you what type of signal it is and an end tag at the end. And so you can just remove that when you have the data. Now in main.h, I do have this assert handler defined. I'm not using it anywhere. Be a good place to use with that buffer, reusable buffer structure in the init function to make sure that length isn't greater than capacity. But since I'm really not using it, I'm not doing it, but it will print out and assert to whatever you're using for a console, whether it's UART or semi-hosting. And then it'll go to the error handler in your main. So then going back to the when you're gathering the data and creating all of the training and inference data for the first time, if that's what you want to do, like I said, you don't have to do that. The model that's checked in is trained, and you can just put it in. It's already in self-diagnostic mode, and you just can run it. It'll gather fresh data off your board and do the inference. And I'll show you that in a live demo, but I'll show you how I created it. So here's my project, and basically the most important part's the signals. And I have 1, 2, 3, 4, 5. I have 6 signals. Now the last one I didn't use this signal clean, which is a combination of all of them. I used just the more specific for each signal. And then what you do is you benchmark, and here's the results of my benchmark. See, there's very few outliers here. It's got a 91 point quality index, and a recall is at 95.2%. Recall is the proportion of actual positives that are correctly identified as positives. It measures the model's ability to detect positive instances. The metric is based on the average of all cross-validation folds. Anyway, this is a nice graphic. It shows you where the outliers are and so on. And so when you go to validation, that's where you think, here's the best one, and this is the one I selected, this FIS VDD. And then you click on deployment, and I just kept the defaults. You don't have to worry now when you do anomaly detection, it has a knowledge checkbox. You get that automatically with outlier detection. So you say deploy, get the library, it's compiling it just takes a quick second. You save it, and it's a zip file, and then you save it. I'll save it to my downloads. So here it is. I'll extract everything. And so knowledge.h goes into your include directory. Lib neai.a. I created a lib directory under core. And then nanoedge.h also goes in your include. And then inside your project, you'll have to include, here I'll show you that real quick. You should know how to do that, but I'll show you real quick. So you go to your project, and you go to properties, and you go to C++ general, symbols and paths. And so you have your library paths. Now this one's hard coded, okay? It's because I created this new folder called lib, and the IDE wasn't picking it up, so I couldn't choose it as a workspace path, so I hard coded it. So just keep that in mind. You'll have to change it. And then the library, here's the trick. You don't put in the full name. You don't put in lib neai.a. You just put in neai, and that's it. And so then that works. Okay, so on the left we have our IDE, and the debugger is stopped on HAL and init. And on the right we have Jonathan Valvano's Texas display, COM reader. And so let's see, we'll set settings, and I'm set on, my board is set on COM5. So we say OK, and then we open the port, And so there's a little bit of leftover from the UART buffer. So anyway, we'll just step through one at a time here. Go through the inits. It's going to jump over. And so now we're in self-diagnostic mode. So now we are feeding that knowledge array in knowledge.h into our model. And so now this was what trains it. So now it's smart. And so this is some normal output that I don't necessarily turn off. And so in this mode, it's not going to pipe anything out unless there's an anomaly is found. You can change that if you want. I have a total, though, at the end. So all of these are, there's no anomalies found. And also, if you want to know how you're doing, I got the total outliers and total pass in the debugger, so you can watch it happening while they're going. Core temp takes a bit. Not as much as clock drift, though. So I'll pause the video for this one. Okay, it came back. I'm waiting a half a second between each iteration, and since there's 128, that's 64 seconds. So it's, you can comment this out if it's not worth it to you. And so here we're going to print out the results. And let's see if can we make this bigger. Not sure, but down here. Total outlier 0, total pass 8. Now if there were an outlier, it prints out the entire 128 values, like I said. So it's all there, and you can tweak it if you want. So I think that's it. So I will leave a link to the GitHub. You know, my GitHub repository is github.com/SteveMac321. That's STEVEMAC321. I have a lot of stuff up there, but I'll leave a link to it. I've got my instructions it talked about. I'll check that in, but the README tells you a lot too. By the way, there's also a YouTube video put on by ST Electronics on anomaly detection. That will be very beneficial. I have a link to that in my anomaly detection repository. So, okay, we've been going on for 18 minutes and 46 seconds, so we kept it under a half hour. So anyway, I think that's going to do it. So thanks for your attention, and if you have any comments, or if you want to make a comment in YouTube or make a comment in GitHub, I'd be appreciated. So thanks for your attention.